Now, the next video, we will show a test. First on laboratory specimens and then on a real structural element. Well, now we are going to describe how we run a test on laboratory samples. Later we will show a test on a real structural element because this is a non-destructive test that can be applied on site. First of all, let me show you that the dimensions of the cell are: the inner chamber has a diameter of 50 millimeters, the outer chamber of 100 millimeters, and the total width of the cell is 110 millimeters. Therefore, we need samples which have at least 150 millimeters of size. So here we have different samples that I will describe. First of all, we have a cube, 150 millimeters cube, which is the ideal specimen for laboratory test. Why? Because if the cube was cast in this direction, we have 4 walls that are nominally identical, so we can run 4 tests on the same specimen. Alternatively, we have cylinders. The cylinders of 150 millimeters diameter are also suitable, but we have to consider that in a long cylinder, the quality of the top surface is different or might be different to the quality of the bottom surface. So it is not totally correct to mix data obtained on both faces. A practical sample is this of 150 millimeters diameter and 50 millimeters thickness. The first thing we have to do before we start the test is to measure the moisture of the surface of the concrete, and for this there is a series of instruments of the Tramex family which we found extremely useful. For example, we can measure the moisture of this element. You can see the value. This is an analogic instrument, is 4.5%. This sample has a moisture of 1.8%. This sample has a moisture of 4%. I will refer to this small sample. It's very common nowadays to use cylinders of 100 millimeters diameter for testing concrete. In order to use the instrument, we have to interpose an adapter which has a diameter of 38 millimeters in the inner chamber and 76 in the outer chamber, in order to be able to conduct the test on this small sample. It's important that the result needs a correction by a factor of 1.73 with this type of adapter. So now we are ready to start a test. Let's start testing a concrete with a high permeability, which is this disc. Very important is that after measuring the moisture, is that the surface has to be cleaned with a dry sponge or this brush to remove dust. But if the concrete is very dirty, like for instance in rough floors which accumulate a lot of dirt, then we recommend to clean first with this vacuum cleaner, like this, a portable vacuum cleaner, and later finish the operation with the brush. Now we are going to show a test on this disc, which is of high permeability, to have a short test, and later we will do another test with another sample. Well, now we are going to run a test on this disc, and we press the icon corresponding to the test. Before we do the test, I show the specimen. It's a disc of a thickness of 50 millimeters and 150 millimeters diameter. The moisture of this sample is around 2%. So now we can run the test, for which we press the start button here. Now we have to place the cell when the alarm sounds, and then we press the button and the test is started. So you see that we have vacuum here. The atmospheric pressure is about 1007 millibars, and the pressure of the two chambers is shown, which is around 30 millibars. It has to stabilize around 30 millibars. Here we can, if we want, we can include some information about the test. For example, we can put video, and we can say, here you can describe the sample, which is a disc. Now, after 60 seconds, we have to press. After 60 seconds, now the inner chamber has been isolated from the pump, and now the pressure starts to rise due to the air in the concrete pores flowing into the cell. And now, every 15 seconds, the increase in pressure is reported in this numerically here and graphically in this chart. This chart has in abscissas the square root of the time, and in ordinates the so-called effective pressure increase, which is the increase in pressure that is measured, like in this case 10.6 millibars, minus the value that was measured during the calibration at the same time. So that's why it is called effective pressure. This is you can see there are guiding lines, so we know that the value will be about a bit higher than 10 to the minus 16 square meters, which is the scale, the units in which the data are reported. When the test reaches 20 millibars in effective pressure increase, the test is stopped. And the value is reported here. So the value is 3.11, and the penetration of the test is 59 millimeters. Now, as the sample has only 50 millimeters, we have to make a correction for thickness. And therefore, here we enter the value of 50, which is the thickness of the element. And then instead of L, we have E here, is the thickness of the element. But also, the sample was very dry, so we have to make a correction for moisture if we want. It's optional. So we can here put 2% of moisture, and then the value is reported here as KT5. Is the value corresponding to a 5% moisture instead of 2. So you see there is a big difference. And with this, if we are happy, we save the result by pressing this key here, and now we simply press this button to release the cell from the sample, and the test is finished. In what follows, I will show the result of a concrete of low permeability to show the difference. We clean the surface of the sample. We press start here, and we place the cell in position and press the button on the cell, and then the test is started. And now this test will take a long time, perhaps 10 minutes, but we will see that we can stop it at 6, depending on the results. So here we have again video, and we can put now, I don't know, cylinder or the big sample. There are 39 seconds, 40 seconds. At this moment, the two cells are evacuated by the pump. At 60 seconds, as I said, the central chamber is isolated from the pump, and then the pressure starts to grow because air is flowing into this chamber, which is now isolated, and then the pressure will grow. And every 15 seconds we have a value of the increase in pressure numerically here and graphically in this chart, which I explained previously. Now you can see the values quite at the bottom of the scale because the permeability is very low. The problem with this is that in order to reach the 20 millibars, it will take a very long time. Therefore, the test is stopped at 12 minutes or optionally at 6, as I will show in a few minutes when we reach the 6 minutes of test. We see the value is roughly about 0.01 in these units, 10 to the minus 16 square meters. Well, after six minutes of test, the instrument gives the user the option of stopping it at 6 minutes and provides a value of, in this case, is 0.012, 10 to the minus 16 square meters. Now, if you see that the chart is quite linear, I recommend you to stop and store the value of KT6. In this case, as is the demonstration, we will leave it run till the end of the 12 minutes. In general, in order to save time, I take the value of at 6 minutes. I want to mention that at this moment the alarm has been deactivated in order not to interfere with the video and the speech. But at 6 minutes a brief alarm sounds telling the user that the KT6 value is available. And at the end of the test, at 12 minutes, a more continued alarm will also sound, telling the user that the test has finished. Well, now, if you see in the clock, we have reached the 720 seconds or 12 minutes. The test is stopped, and now the value reported is 0.010. The KT6 was 0.012, so you see the difference is very small. So we would have saved time if we had adopted the KT6 value. So we made no correction here, and then we save the value as it is, and now we press the button here to release the cell. And with this, the test is finished. In the next video, we will run a test on a structural element in which we will show the advantage of the facility of using a smartphone as remote control to operate the instrument.